Hello, welcome everyone. A very warm welcome to everyone, attendees, organizers, speakers, to our little presentation. Today we are here presenting on a topic which we have worked on since like the past 2 years, and this is an approach and attempt to show you how does one, try to ensemble different neural networks, deep neural networks, and and what are the consequences and the benefits of it. So throughout this talk, what we'll do is we will touch upon how it's done, and more importantly, what is it, and then we'll move on and go ahead to telling you the challenges we faced across the ways, the applications, and why is it important. So without much further ado, I welcome you all to my presentation, and let's introduce ourselves, I guess. So I'm the one on the left. My name is Dipam Paul. I am a final year undergraduate student. I belong from the city of Kolkata, and that's a picture of my city. Not taken by me in particular, but again, a picture nonetheless. Uh, I am a final year undergraduate student, like I said. I am currently working as a research assistant in Emory University. And well, that has been my journey all throughout. I work in areas of deep learning and medical imaging. And now my co-presenter would introduce herself.
Namaste. My name is Alankrita Tewari, and I'm from the city of Lucknow in northern India. And again, that's a picture of my city. And I am also a final year undergraduate student pursuing my bachelor's degree in the field of electronics and telecommunication from KIIT University, Odisha. Now, this is going to be my second PyCon. I have earlier presented at PyCon US 2020, and I really look forward to having a very interesting and fun-filled learning experience with all of you. Now, moving on, I would start by, giving credit where it's due. We thought that we should take a moment to talk about the history of medical imaging, without which we wouldn't be sitting here, presenting on this very same topic. Moving on, I would request all of you to take a look at how this journey of medical imaging started with radiography back in the late 1800s and have, transformed into so much more since then, with the hard work and input of all these great minds throughout history, so that now we're in a time where things like CT scans, MRIs, X-rays, OCT scans, everything is possible, and it has made medical imaging a field with so much scope and so much areas of research. Now, moving on. To answer this question, why use an ensemble after all, we would want you to first understand what we mean by ensembling. Now, the ensemble word in itself, in its most literal sense, means amalgamation of two or more objects, right? So taking that into the context of medical imaging and computer vision and AI in general, what we mean here is ensembling of neural networks to create a model which outperforms the neural networks when they're implemented individually. So that is the idea where it comes from. And how we stumbled upon this idea, in particular, is when me and my co-presenter were working on the various problems in the domain of medical imaging. For example, detecting various retinal disorders from OCT images, or while detecting parasitized malaria from cellular images, which again is a binary classification problem, or a multi-classification problem of classifying skin lesions into 7 classes. Now, one thing that was common through all of these problems was that when we were using a single deep neural network for, coming out with a model that's robust, what we faced was the problem of overfitting, for example, or the problem of our model not being reliable enough. And that is when it, came to us that we should, just do something with, different models and try to make them more compatible and then come up with an ensemble network. Now, having said that, I would like to talk about the connection of the problem with the Indian subcontinent, or the medical situation in the Indian subcontinent, because that is what we are very familiar with, or that is what we can connect with. The first problem that I would want to talk about is the problem of variance, or the problem that occurs in different deep learning models or neural network models when they're presented with unseen examples or new examples. And that is what we essentially want for in order to make our study or our model implemented in the clinical setting. So that is the first problem, or the first uh, obstacle that we had to overcome in order to make our study more reliable and robust. Having said that, the second problem in itself stems from the first problem, meaning that if when presented an external or an unseen example, if our model is not able to uh, predict the result correctly or classify it correctly, then it overall hampers the reliability quotient or the trustworthiness of our model. And the third most important thing that we wanted to solve was the problem of absence of implementation of the entire study in clinical or in medical structure. And that can be due to various reasons, and the most important of them being was the apprehensiveness or the reluctance that we encountered from the medical personnel, because of them not trusting the models completely, or them being afraid that you know uh, the artificial intelligence in the medical domain would later on take over their job or their means of livelihood, which again is not at all what we intend to do here. And there's something that we would want to make very clear, that no amount of study or a model or a artificial intelligence uh, application in medical science could overtake the expertise that a, let's say, experienced doctor with an with the experience of, let's say, 20 to 30 years has. And yeah, that is something that we really wanted to make clear. Now, moving on, I would like my co-presenter to take the presentation forward from here on.
Correct. Thank you so much. That was very wonderfully put. So now let's move a little to the algorithm at hand. All right. So, this particular study was, of course, built, and it sort of got motivated because of the reasons that were mentioned in the previous slide by my co-presenter. Now the question comes: what did we do? I think the question most of the deep learner researchers would be interested in. Okay, so first let's clear something out. Okay, so we did tell you that we have tested this model and validated this model in 3 different type of studies. First was malaria, and first I think was OCT images. Second was malaria, and third was lesion net, which is the classification of skin lesions. But what we do here when we try to demonstrate this particular process, we take the first test case of classification of OCT images, which is optical coherence tomography images, wherein we have different retinal disorders, and we sort of have a model built in order to classify the same. Now the problem sort of comes when we sort of try to investigate through the data set, where in the data acquisition process, where we sort of figured out that our data set, the retinal disorders, which we'll come to a little later, are very overlapping in nature, as in they are really overlapping. They do not cannot, probably it's impossible to distinguish them with the naked eye. So that's a problem. That's genuinely a problem. Even for a doctor, I guess that's a problem, because we can only do so much. Human eye cannot probably distinguish a pixel from another pixel. We can see if two things are visually different, a flower from an orange, for example. Anyway, so this is the workflow that we designed, where we sort of first collate the data from a place called Mendeley repository. Then we pre-process the data. Then we have these 4 architectures, combined together, ensembled together, and finally we validate the model. Now, there are a lot of questions here. Why these 4 architectures when we could have had, our model built with the rest 400? Okay, so we'll go to that in a while. So firstly, the entire pedagogy that was followed here has been divided into 2 phases. This is the phase 1, where we train an inference, insights out of the model. How do we do that? We firstly see how well different architectures perform on our entire train set individually. So for this study, when we tried to classify OCT images, and we also documented the same, we'll like show you a snapshot of that too. So these are the architectures which like prove to be really efficient and optimized in this particular study. So namely DenseNet, which is 16, Inception V3, Custom CNN. Uh, the Adam optimizer was, as usual, probably the best performing optimizer that we tried on in this particular data set in this study. However, we would also like all the audience here to note that since we use these architectures in this particular study, it does not cater to the fact that it will be the same for any other study. It might just be different. The number of architectures might also be different, because the factor of compatibility does come into play here and plays a very big role than we should have realized previously. But again, we will learn the hard way. Nevertheless, so these are the scores. These are the scores of the phase one. These are the different architectures and the different metrics on which these architectures were tried upon. Again, these are the scores on the test set that we received of our data. And moving forward, this is the phase two of it, and I think this is the contribution. This like delineates the contribution that we had in order to build the ensemble model using the last four architectures that we talked about. Okay, so this is the algorithm, right? So what we first do is we take the deep neural networks. You can take as many as you want, as less as you want. It's upon you. What we do is, so according to the results that we get here, we sort of assign nonlinear weights to these models. And thereon, we sort of, first go ahead and design and train the ensemble model. And then what we do is we sort of freeze all the layers in the ensemble model except two, fully connected and dense. And then we again train the ensemble model using the frozen layers. And then what we do is we finally validate the model, of course, on unseen examples. And this is the algorithm. If you just want to have a look for a little more time. After this, let's move forward to one of the most important parts of our project. So why did we choose to do this? I think that's very important. Okay, so number one, in this field of study, especially in the medical domain, which again I would say our project or our contribution is not just restricted to, it's just a place that we thought probably would be the best to sort of start out and implement what we have designed for, and also like contribute a little bit to the solving the problems around the world. So yeah, so the deep learning researchers always have a habit of attaining state-of-the-art accuracy, and we can guarantee that with our project. How do we do that? How are we so kind of confident? Well, so central limit theorem tells us that like when you combine different architectures, the collective accuracy of the combined architecture will always and at all times be greater than the individual architectures at any, considering two things. Number one, you keep the training set same, and number two, of course, the compatibility of the models that you're using. So that's guaranteed here, because of course you're taking 5 or probably 4 or 3 of the best architectures that perform the best on your dataset. So the combined accuracy is supposed to be higher than each of the individual ones. Second, as my co-presenter previously talked about, the variance problem, we take care of that because our model has been proven to work excellently well, especially on very unseen examples, which are not a part of train set, which were definitely not part of the train set. And third, which was again proved experimentally, about the problem of overfitting. We sort of will show you the performance analysis, and we'll show you how our model did not overfit. Although our model did overfit, but the ratio was very less, as in it probably overfit like 1 out of 15 times it was trained on. So I think that's a very good step and a starting point in a very positive direction. So now, with these being done, let's move ahead to a little bit of performance analysis of why probably laying down the evidence of what we are saying here. Okay, so this is probably the most popular statistical test there is, which is the confusion matrix. Now, this confusion matrix was laid down on the after the classification made on the test set, and now these are the accuracies. So our model, in fact, was proven wrong only 1.47% of the time on the entire test set, and it proved out to be true 98.5, a little more than that percent of time every time it was sort of validated on external examples. And I think this indicates a very strong point when it comes to the problem of variance and model reliability. So this was the confusion matrix. And now, yeah, the overfitting problem, right? So as you can see, the loss curves have been delineated here, and I would request the audience to sort of see the convergence of the loss curves and how it's sort of yeah. So that does tell you that probably the model is not overfitting, and the final model was of course trained for 250 pox, and the accuracy curves have also been shown here for you to have a better idea of how well our model worked. And yeah, I guess these are the tested out results. Moving forward, I think my co-presenter will take up from here, tell you a little bit about results, and yeah, we'll meet again.
Thank you, Deepa. Now, moving on with the representation of the results we got in the, all the steps that we performed earlier. I would like to, tell you all that what we did was we made sure that we represent our results in two different formats. The first being the grid presentation, grid representation, which again is a very important method of representation in the research perspective. How so? I'll explain it. What we did here is we took a random batch from our test set, and here we can see that the mislabeled or the miscited data is been labeled in red, and that the correct data or the correctly cited data has been labeled in blue. Now this sorts of tells us that tells us about the performance of our model. And now moving on to the predicted result representation with confidence scores. Now this representation is very important when we talk about the implementation of this project in a clinical in the clinical perspective. And how so? Like from a doctor's or from a physician's point of view, what we do is we take a random unseen example and we sort of test it with its respective confidence scores, which again tells us the probability of the prediction being right, and in turns again tells us about the reliability of our model and making it more robust and more dependable in the clinical point of view. Now moving forward, what we did for the test case one or the OCT study that we performed, we have made a comparative study to show a comparative analysis of what we've done and how our model is better than all the benchmark studies that have been done in the same domain. Now talking about the first study, the Karmani et al. Study, now this is a benchmark study in this entire domain. And how so? This study is the one that's responsible for the fashioning of the data set that all the studies, the three studies that you can see here, have tested their models on. They made it possible for the research to be done in this specific domain and make it possible for us to sit here and discuss this particular topic. Now, the second study that we're going to talk about is the Rastogi et al. Study. Now, this is the study which inspired us to take upon this problem and solve it in our own unique way with bringing in the concept of ensembling deep neural networks like we did. What they did was they took a single deep neural network, the DenseNet, and they performed the classification problem on the same using the same single pre-trained model, and were able to get the results in the metrics that I've shown. And we, after ensembling different deep neural networks the way we did, were able to outperform all of their studies, as it is clearly seen from the table presented. Moving on, we've already added the links to the specific documentations for your interest, or if you'd want to, delve deeper into it or read into the subject matter yourself. The first one being is like the study that was authored by me and my co-presenter for the 33rd IEEE CBMS conference, and we would encourage you to go forward and take a look at it and give us a feedback, or if you have any questions, then talk to us about it. And the other two studies are the ones that we talked about, the Rastogi study and the Karmani study, respectively. Now, moving on, I would like my co-author, my co-presenter, to take forward the presentation once again.
Thank you so much. Okay, so moving on to the hard part, I guess. So these are probably some of the most planned enhancements that we had in mind while preparing this presentation for you all. So, of course, these are some of the most real problems that even we would, love to work on if given an opportunity, because these are things that we face along the way. And these are, often underrated challenges, but these are very important ones. So the number one challenge is the fact that there is no thumb rule. Okay, so there is no thumb rule. There's no mathematical expression which sort of tells you that probably if you have a certain amount of training data available, how many models will be the best fit for you to ensemble your training data on. So there's no mathematical expression which tells you the number of ensembles that you can use versus the amount of training data available. So that's sort of a problem, because there are so many models, and the road to optimization is really long, and you have to just go ahead and experiment things out, and that's not very time efficient, I would say. So it would be really nice to have a thumb rule determined, and I guess by the next time I meet you here at PyCon Australia, probably will be a step ahead in that regard. Secondly, faster computation with lesser reasonable resources, of course. So when you have increased the model numbers, your compute that you will require in order to train them, validate them, will also sort of have increased. But I guess with time and the advancements in the hardware industry, and especially the GPU industry, I don't think this is a problem which is going to last long. But again, thing to ponder upon, I guess. And third, of course, who doesn't want better optimization? You will always have better optimization in our opinion when you have models which are compatible with each other. Now, what is the yardstick with which you determine compatibility? Results, how well your combined results are, because they are the ones which at the end of the day speak to you about if you did what you did, if it was right or not. So optimization, very important, and thumb rule, and of course less compute. Okay, so now moving on, I would request my co-presenter to take it from here.
Right. So now we're at the end of our presentation, and we would encourage all of you to write to us at the given email addresses if you have any questions, any doubts, or anything you want to talk to us in general about regarding our presentation or otherwise. We really look forward to connecting with all of you, and thank you for this great opportunity of for being able to be a part of PyCon AU 2020 and presenting in front of all of you.
Right. I would also take a moment to thank the organizers of PyCon AU 2020, who has made this entire thing possible, probably in the most unfortunate of times in our lifetime at least. I would like to take a moment to also thank the speakers and attendees of PyCon AU 2020, because without you, I don't think this entire event wouldn't even have been possible. And lastly, of course, the men and women of the hour, to everyone who work day and night to sort of make this community brighter, bigger, and what it is every day. I thank each one of you, and we both collectively hope to see you again in some other conference, and hopefully again next year in PyCon AU 2021, and again hopefully not in an online setting. So thank you so much, and have a great day ahead.